million if you want to be on the safe side. So no, I can't say this. And because I'm just doing this on the fly, and that's alright, you guys can do it too. This is bounded by a constant times r to the fourth for some constant c, and you can find one that's going to work. So that means your g. So your function g of x is c x to the fourth. So delta is going to be g inverse of epsilon, which is going to be epsilon over c raised to the 1/4 power. It boils down to, again, using a definition of limit like in the first problem, but because you're working around showing differentiability at a certain point, you need delinearization, and you need to rewrite it in such a way that introduces x minus x naught and y minus y naught to do everything in terms of that. And you might find it easier to work in terms of these variables like z and w as well. It's going to be a term of lowest degree that's actually going to be dominant. What definitely would work is 26r for r less than 1, 26r to the fourth for r greater than or equal to 1. Just because of what happens when r is less than or greater than 1, how all these powers of r behave. So it's like a piecewise function.
Right.
So it's something that looks like this, and then shoots up. And it's definitely going to be bigger than the whole thing, but bigger than the original function. So it muddies the waters a little bit, but this is a function that still has an inverse. But what we really care about is this case. We care about what's happening when r is going to 0. So it's the lowest power of r that determines the rate in that case. 26x. If x minus 1 squared plus y minus 1 squared square root is less than delta, and you're assuming that delta itself is less than 1, which is really what you would be concerned about anyway, then f of xy minus L is less than, so that's going to be 26 delta, which is 26 epsilon over 26 is less than epsilon. And it's choosing 26 because it's the sum of the coefficients. So when you start studying running time with algorithms, you have to think backwards. It's highest power that matters. And A, so I mentioned use a limited continuity to prove that this function is continuous anywhere. And so starting with the definition of continuity, what you need to show is that the limit as whatever point P approaches P naught of f of P is equal to f of P naught. That's what continuity means. However, I would suggest looking at it a little differently. Just a simple rewrite of this. Think in terms of this going to 0. Because then what you would do is, so by the definition of limit, so you assume that epsilon is greater than 0. You want to show that if the distance between P and P naught is less than delta, then f of P minus f of P naught is less than epsilon. Now you would arrive at this regardless of whether you looked at it this way or this way, but looking this way sets the stage a little more nicely. You're applying the definition of limit in a similar way as to the other two problems we're talking about. So in other words, this exam is giving you a whole lot of practice with this definition. So you need to bound this in terms of the distance between P and P naught. But that's done for you in the statement of a problem. Unlike the other two problems, you don't have to go through some algebraic rigmarole to get a hold of this function g that we've been talking about. It comes from a problem statement. Similar idea. You have to show that if that exponent alpha is greater than 1, then the function has to be constant. In other words, show that its partial derivatives have to be 0, and there's no other choice. Try actually computing df dx, df dy using the definition. So fx at some point p is equal to the limit as h goes to 0 of f of p plus h times the vector I, or I is the vector 1, 0, minus f of p over h. And then there's a similar definition for partial with respect to y, only being the vector j instead of I. But what do we have here? difference between function values. You go back to what the problem is saying about how the difference in function values relates to the distance between the points to our functions being evaluated. Because if we look at this difference of vectors, p plus I h minus p, well, that distance is h, which is exactly what you have here in the denominator, which works nicely for you. And it's essential that the exponent alpha is greater than 1 for this part, otherwise it's not true. Once you try applying the definition of limit to this, and that means trying to bound this in terms of this distance, which is h, then when you look at what's given, the information given in a problem, then you'll hopefully be able to see why this works out. Mind is, if you have h to some power q, that goes to 0, as h goes to 0, as long as q itself is positive. So that's all it takes for that to work out. Say q is 1/2, so the square root of h is still going to go to 0. It'll go to 0 more slowly than h, but it's still going to go to 0. If you look at it this way, that the equation is, then yes, for partial derivatives of z with respect to x and y, then there's this formula, and similar for dz dy. So I just recommend doing it that way. Now, when you're doing implicit differentiation, that is what you're computing. But when you do implicit differentiation as we normally learn it, you're very prone to mistakes. So I would just try partial differentiation on this guy with respect to x and respect to z and y, and then you should have a lot better chance. Bonus, I guess bonus number 1, because it is the first one of the two that I came up with. If you have a situation like you have a vector x that's x1, x2, up to xn. So how do you express the partial derivative of that? Actually, let's make it x squared. So we're squaring all these components. So if I'm differentiating xi with respect to xj, well, it's not so easy to express, because that's going to be equal to 1 if I is equal to j, and it's going to be equal to 0 otherwise. You end up having a lot of situations like this that are kind of a pain. There is a notation that you can use, can help you out a bit. So this symbol, delta ij, is used to encapsulate all of this just in one symbol. It's called the Kronecker delta. So it always has these two subscripts, I and j. So this is equal to 1 if I is equal to j, it's equal to 0 otherwise. So what I'll do, I'm going to take a small piece of it and do it for you. Let's suppose you have a function g of a vector x, and it's equal to the dot product of x with itself, which is the same as x transpose times x. So that would just be x1 squared plus x2 squared plus xn squared. What would the gradient be? What would the partial derivatives of this function be? So you got to differentiate it with respect to each of the x's, x1, x2, and so forth, to get all the components of the vector. Yeah, so more conveniently expressed in vector form as 2x. So this is part of a function that I give you, but the other part, that's a denominator. The numerator is where there's a matrix stuck in here. So if you have x dot product with a times x, so what's going to happen is you can write this as a summation. And you know what? I might have put this in the problem as something to do. I don't remember, and right now I don't care, because it's not the main part of the problem anyway. So this would be equal to aij, the entry in row I column j, times xi times xj. How do you compute the gradient of that? That's why I recommend trying with a small example, just to see how it might work out. How does the gradient of this relate to x, or a, for that matter? And here, we have a simple relationship between the gradient of this function and x, it's just 2 times x. The question is, what happens in this case? And if you try with a simple example, you just might be able to see it.